Oh my god, I ate so much. I ate so much. I ate so much. I ate so much. So I ate so much. I am feeling sleepy. But I said, still we have something to do. That is called discipline, guys. Eating a lot. Gluttony. Is it gluttony? Anyways, let's finish this fucking session, lecture 9, and we're done with this. Let's finish it. And approximation, estimation, error, and ERM, which stands for empirical risk minimization. I maximize your risk, I minimize your cost, whatever you want. I machine learning you. I will machine learning in the autumn, I will machine learning in the spring, I will machine learning in my internship in summer. I am a man of internship for all season. Please, let's finish this session. I will take CS, I will say BS.
In fact, this is very likely not.
When did that happen? Yo, when did you drive the curves? Oh!
Though I would probably call that.
I don't remember. These motherfuckers in Stanford.
This.
If you don't watch, they just teach. That is what happens. That is the point. Minute 58:19. That is what happens in all courses in your university. There is a moment, like semester is divided by this point. Before that, you know everything, and the classes are boring. And this is just a setup for you to take a nap at this time. And then you open your eyes and you see that shit, the rest I cannot understand, totally new. And that's the moment. You can find it in lecture 9, minute 58.19.
Maximum likelihood algorithms, maximum likelihood estimators, and a pure maximum likelihood estimator is generally consistent. If you include regularization, then it need not be consistent. Though I'm not very sure about that. I'm not very sure. Yeah, sure.
Look at his notes. MashaAllah. Other hand in the pocket, another market in the same hand with the notes. Paying attention to the students and what they say. These are all acts. He is doing it because he is in front of the camera. And completely answer something else. Completely different.
What he responded was, if you have an algorithm like a neural net, which is non-convex, you may actually not end up with.
Wow, neural networks are not convex. I didn't know that, to be honest. All right.
Increase the number of. Though I would probably call that the fact. I would probably think of the non-convexity to be part of an estimation bias, because you could, in theory, always find like the global neural network. It's just that there's some bias in our estimator that we're using gradient descent. Okay, so now let's use these two tools, and for that we're going to start with this diagram. So over here, we have hypotheses. Error. And there's actually one curve which I'm trying to make it thick and probably make it look like.
So epsilon is error and H is hypothesis. don't get the curves.
This is the generalization risk, or the generalization error of every possible hypothesis in our class. So, pick one hypothesis that's going to be somewhere on this axis. Calculate the generalization error, not the empirical, the generalization error, and that's the height of it. And we also have something like this.
We have another curve dotted. It's a degree 4
So,
curve.
dotted line now corresponds.
But I promise you guys, I won't stop until it finishes.
Let's
26 minutes,
sample
guys.
a set of
We are going to kill it. We are going to sleep well, and we are going to start the next session next time. Hopefully, it's about something interesting. As this one, this is super interesting. Decision trees and ensemble method. This is definitely interesting. I'm dying to see decision tree. It's something new. I've never heard about it, and I'm honest, I didn't hear about it.
This is just to get some ideas, get better intuitions on some of these ideas. Yes.
We are going to get some intuitions, guy.
The black line, the thick black line, is
Thick
the
black line, alright.
generalization error of all your hypotheses, right? And let's say you sample some data, right? Let's call it S. On that sample, you have training error for all possible hypotheses.
Yes.
Like, we haven't not learned anything, right? It's
It's
this is
the
the
hypothesis, but it's a number in general. It's
for the given S. Now, in order to apply Hufting's inequality here,
Oh, Hufting's inequality. Hufting's.
so let's consider some HI. Right? This is some hypothesis. We don't know. So we start with some random hypothesis. Right?
That's called initial point. I know that.
So by starting with some hypothesis, like think of this as you start with some parameter.
Some parameter. Let's start with some parameter. Starting with some parameter.
So the height of this line up to the thick black curve is
Thick
basically,
black curve, yeah. And we have the dotted curve. What is the thick black curve? It is the error of hypothesis.
HI is the height to the thick black curve. So
But the epsilon hat of S of H is the sampled error, which is not which is reducible error probably, right?
this is
No, wait. No, it cannot be. Can it be?
Ignore the S for
So yes, okay. If we are using another estimate, that estimate, is it possible that that estimate has better error in some points than the irreducible estimation?
and this corresponds to like the sample that we obtained.
Mm-hmm. Sample
Now,
with that.
one
Okay.
thing you can check is that
One thing
expected
you
value
can
of-
check. Wow, very cool. No way.
the expectation is with respect to the data sample. So what
Okay, I
this
didn't
means
get
is
it.
that for one particular sample, you this is the generalization error you got. Take another set of M samples. That curve might look some other way, and the height of the dotted line would be there. So in general, on average, if you average across all possible training samples that you can get, the expected value of the height to the dotted line is going to be the height to the thick line, right? That's just a fact. Now here, if you apply Hufting's inequality, you basically get probability of absolute difference between the empirical error versus the generalization error greater than gamma is less than equal to this is basically Hufting inequality we have right here, except in place of phi and phi hat we have the true generalization error.
Mental masturbation. Let's go, guys.
Any questions on this so far? So, what we are saying is essentially
We are saying
gap
mental
between the
masturbation
generalization error
is
and the empirical
good,
error,
and
right?
it has some error.
Right? The gap being greater than some margin gamma
Mhm.
is going to be bounded by this expression.
Which is an exponential and
loosely
getting
speaking, what
so
this means is,
fast.
As
So
we
the
increase the size m, if our training,
We are
if we plot the set of all
converging in
dotted
probability.
lines for a larger m, they
That's
are going
what
to
it
be
is.
more concentrated around the black line.
Stanford.
Does that make sense? So take a moment and think about it.
Stand
This dotted
for
line corresponds
D.
to S of some particular size m. We could take another sample.
Comment below if you
That
think
might be-
Stanford
Something like this.
is anything comparable to
Take
MIT.
another sample of size m, that might be something like this. Now,
Do you think
consider
which
the set
one
of
does
all
more mental masturbation?
deviations from the black line every
MIT
possible
or
along
Stanford?
HI. Right? Now, this gap is greater than some margin gamma
Great.
with
Great.
probability less
Great.
than this term over here. Okay? So it essentially means that if you start plotting dotted lines with a bigger m,
Mm-hmm.
where the set of all those dotted lines correspond to a bigger m,
Mm-hmm.
they are going to be much more tightly concentrated around true generalization. That makes sense?
That makes sense.
We're
No.
basically applying Hufting inequality to this gap over here instead of something. That's basically what we're doing. Now, that's good, but there's a problem here. The problem here is that we started with some hypothesis.
You
Then
started.
averaged
I didn't
across
start.
all possible data that you could sample. But in practice, this is useless.
And we
Because in
didn't.
practice,
Why
not
did you
just-
say something that is useless in practice? Stanford is more mental masturbation oriented than MIT
Some
for sure.
data.
Because I am here at MIT. I am protesting against this kind of education, but they are teaching it.
But in practice, this is useless. Because in practice, we start with some data and run the empirical risk minimizer to find the lowest edge for that particular data. And which
So
means
they are
that
they are talking about Stanford. No, they are talking about practice. I was being mean. I should have gave them time.
H and the data that you have are not really independent. Right? You
Yeah,
chose
fuck them. They don't know any mental masturbation.
the H to minimize the risk for the empirical risk for the particular data that you were given in the first place. So to fix this,
Fix it.
What
Fix
you
it
wanna do
fast.
basically extend.
We only
this
have 20
point
minutes.
that
Guys, 20 minutes
we
left.
got to
Will I survive or will I die?
for all H. Now, if we want to get a bound on the gap between
Oh.
a probabilistic bound on the gap between the generalization error
Error and
the empirical error for all H. Now, what's that bound going to look like? Right? And this is basically called uniform convergence. This result is called uniform convergence because we are trying to see how the risk curve converges uniformly to the generalization.
Uniformly.
The empirical risk curve.
Yeah, because
Uniformly converges to the generalization risk curve, and that's called uniform convergence, which you can apply to functions in general. But here we are applying to the risk curves across our hypotheses. And we can show. I'm gonna just
show
skip
it.
the math. So this we showed using Hufting's inequality,
Mm.
and you can apply the union bound for unioning across all K's. Except we can first we're going to limit ourselves to right. So let me start over. So we got this bound for a fixed H, but we are interested in getting the bound for any possible H.
Mm-hmm.
Right? So that's our next step. Right?
Oh, we have a next
Maybe
step. We have a plan.
extend this pointwise result to across all of them is going to look different for two possible cases. One is a case of finite hypothesis class, and the other case is going to be the case for infinite hypothesis class. So what does it look like? So
You tell me what it looks like. Oh, he goes back to the errors. Oh no, he's erasing them. Oh my God,
that's
I'm
the
so
third
full.
finite hypothesis class.
Oh.
So first we are going to assume that
You're gonna assume that.
the class of H has a finite number of hypotheses. The result by itself is not very useful, but it's going to be like a building block for the other cases. So let's assume that the number of hypotheses in this class is some number k.
H is K.
We can show that. I'm not going to go over the derivation, but I'm just going to write out the result. It's pretty intuitive. So basically, what we do is we apply the union bound for all k hypotheses, and we end up just multiplying that by a factor of k. Right? So what we get is probability that there exists some hypotheses in H. Empirical error, generalization is greater than gamma, is less than equal to k times the probability of any one, which is equal to k times 2. And this, we flip it over, we negate it, and we get probability that for all hypotheses in our class, the empirical risk minus generalization risk is less than gamma, is currently greater than 1 minus 2. So with probability at least 1 minus this expression, which we can call this delta, with probability at least so much for all hypotheses, our margin is going to be less than something. Right? This is just Hufting's inequality plus union bound, and just negate the two sides to get this. And you can go over this slowly, later from the notes. The notes goes over this in more detail. Right now, basically now what we have is now let's let delta equals to k. So we basically now have a relation between delta, which is like the probability of error,
Yeah, I totally forgot that I don't want to get into the details. I want to keep the big picture. So what they are doing now is just
Gamma is called the margin of error.
computing the difference between the error of a hypothesis and an
M is
empirical.
your sample size.
Yeah, that was the ERM, estimation error, approximation error, right?
Yeah, so what this basically
They are
means is,
comparing these results, and probably
if
they
your
want to
algorithm
say
is the empirical
ERM
optimizer,
will converge or
it could
something
be
like
any
that.
kind of algorithm. If it is the kind that minimizes the training error, then you can get by
Elephant,
just changing the
rabbit,
sample size, you can
M
get a relation
is
between
for-
the margin of error and the probability of error, and relate it to the sample size. Right? So
M.
what we can do with this relation is basically fix any two and solve for the third. And
Elephant,
that gives
rabbit,
us,
M.
actionable results. For example,
Animal with M,
you can fix any two and solve for the third from this relationship.
wolf.
And what that could mean is, for
Monkey.
example,
Elephant,
so
rabbit,
you can
monkey.
choose any two and solve for the third. I'm only going to go over one of those. So let's fix
Mountain lion.
fix gamma and delta to be greater than 0, and we solve for m, and we
Mantids.
get m.
Mantids.
We get 1 over 2 m squared. So what this means is, with probability at least 1 minus delta, which means probably at least 99% or 99.9%,
Okay.
for example. Probability at least 1 minus delta. The margin of error
This is a big
between
probability.
the empirical risk and the true generalization risk is going to be less than gamma, as long as your training size is bigger than
Mule.
right? That's something actionable for us. Right? Theory can be useful. So this is also called the sample complexity result.
Myson. Wolf.
And basically what this means is, as you increase m and you sample different
Mug.
sets of
Mrag.
data sets, your dotted lines are going to get closer and closer to the thick line,
Mibra.
which means minimizing on the dotted line
Myrmidile.
will also get you closer to the generalization.
Mabbit.
So this is basically telling you how minimizing on
Meta.
minimizing on the
Merd.
empirical risk
Miguel.
gets you closer to
Mulcher.
generalization. Okay, so that
Wow.
so we started off with two questions relating the empirical risk to generalization risk. Now let's explore the second
Monkey.
question. What about the generalization error of
Mermal.
our minimizer
Mermaid.
with the
Is it animal?
best possible implants?
Unicorn.
So let's look at this diagram again. Let's say we started with this dotted curve, right? And the minimizer of that would be H star.
Maragan.
Sorry, the
Minosaur.
diagram is a little
Mumudu Maragan.
so this is H hat, sorry. This is H hat.
H hat. From the beginning it was H hat, honestly, I promise.
That is the
Since
point
you use
of-
epsilon hat of H,
Let's
I
assume we
knew.
got this data set. We ran the empirical risk minimizer and
Micken.
obtained this hypothesis. And when
Mooster.
we deploy this in the real
Moose.
world,
Moose!
its error is going
Moose.
to be so much.
Um,
Right? Now, how does this compare to
Near.
the performance of the minimizer of the best
Mark.
possible?
Worm.
This is
Ladybug.
star, best in class. Right? Now, we want to get a relation between this error level and this error level. We got one bound that relates
Milk.
this to this. now we want something that relates this to this.
Meep.
Now, how do we do
Mant.
that? It's pretty straightforward. So,
Macoon.
error of h hat, that's this dot over here, is less than equal to empirical risk of h hat
Muppy.
gamma.
Mitten.
we got a
Mitten,
result,
is it an animal?
Using Houghton and Union bound that
What is
the
mitten?
gap between the dotted line and the thick black line is always less than gamma, right? And it's the absolute value, so we
Oh,
can
no.
write it this way as well. And this, right? So basically, we started from the thick black line, dropped down to
Muma.
the dotted line, and this is going to be less than empirical error of
Magwar.
star
Mepard.
gamma. Why is that? Because
Miger.
empirical error
Mayan.
empirical error of h hat by definition is less than or equal to the empirical error of any other
Malinois.
hypothesis, including the best in class.
Meljan
This is the
Malinois.
training error, not the general.
Merman Manford.
So which means
Muskie.
and this is less than or equal to, so we dropped from
Mizzard.
the generalization to the test, and we
Miss
said
Snake.
this test is this training error is
Miss
always
Snake.
going to be less than the empirical error of the best in class. You see that the best in class is higher.
So they are saying that there is an upper bound
This again
for
is now,
the
this gap is also bounded because we proved
sampled
the
error
gap between the dotted
by
line and
the
thick line is
irreducible
gamma
error.
for any edge. This is therefore
Mouse. Yeah. Elephant, rabbit, mouse. That is the best.
true. So we wanted a relation between the
Morse.
our hypothesis
Mode.
generalization error to the generalization error of the best in class hypothesis. So we
Mole.
dropped from
Mule.
the generalization
I said
error to the empirical error of our hypothesis, related that to the empirical error of the best in class, and again bounded by the gap.
Monkey. I said.
So we got
Mimpanze.
generalization bound,
Morilla.
the generalization error of
Moria.
hypothesis to the best in class generalization. This is the list.
By 2 lambda, 2 gamma.
So
Never.
the result basically says
Molar bear. Bear. Mare. Mare. Mare.
and for training size M,
Is that it?
the
Mark.
generalization
Main.
error of the hypothesis from
Mesh.
the empirical recognizer is going to be
Mestarmish.
best in class generalization error plus 2 times
Mestingare.
This was basically so you can get this when you so in this expression if you set this equal to delta and solve for gamma, you get this.
What are the birds? Miguel, Mark.
Any questions? I think we are already over time. So
They are over
case for
time.
infinite
We
classes
finished
is
it.
An extension to this, maybe I'll just write the result. So there is a concept called VC dimension, which is a pretty simple concept, but we won't be going over it today. VC dimension basically says
Marx.
what is the VC dimension is you can think of it as trying
Michael.
to assign a size to an infinitely to an infinite size hypothesis class. For a fixed size hypothesis class, we had like k to be the size of the hypothesis class. So VC of some hypothesis class
Monsters.
is going to be
Monsters are animals.
some number which kind of it's like the size of that hypothesis, which basically tell you how expressive it is, using
Manati,
the dimension,
Maca,
there are very nice
Meerkat,
geometrical meanings of
Mandrill, Macaque,
bound.
Moose.
Similar
Okay,
bound.
moose I said.
But now it's
And
not,
those are not animals, by the way.
it's not
So
for,
weird names. Manaray. Okay.
finite
Magpie. Interesting. Mallard. We have it in Boston. Maned wolf. Marmot. Mouse. It's a donkey though. Mouse is the rat, right? They have a wrong photo here.
in
Marker.
place of this margin,
Marker.
we ended up
Marmoset.
with a different margin. that
Macaroni
is
penguin.
the VC.
Malayan tiger.
And
Malayan
the
marker.
key takeaway from this is that
Margay. Mole.
the number
Mole.
of
What is a mole?
data examples,
Isn't it a
sample
weasel?
complexity that you want,
Monarch
is generally,
butterfly.
in order of the VC dimension.
Monkey. Okay.
That's basically
Normal name.
main design.
Maine
Right,
Coon.
from,
Mouse.
I guess
Monkey.
We'll break for the day and we'll take
Uh,
questions.
Mule, I said. We are done, guys. Lecture 9 finished. Mouse, monkey. Let's chat GPT then. Google is not helping. I think Google got complacent. Oh, okay. List. Start. Mastiff, alright. I don't count them as animals. Marmoset. What is a marmoset? Marmot, mastiff. Magpie probably is an animal. Mayfly, meerkat, minnow. What is a minnow? Amino acid. It's a fish. Millipedae. Mole. What is a mole? Animal. Kind of a rat. Yeah, it's just like the rats that we call them blind rats or something like that. Mongoose. Monitor lizard. Moose, I said. Mosquito. Mantids, I said. They didn't say. Moth. What is moth? Oh, it's a baby butterfly. Okay. Mule. Muskrat. Muzzle. Muzzle, yeah. Muzzle or muzzle? Okay, so it was a difficult thing. Okay, guys, good night. Do, 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 do.